Hi, welcome to another IGCSE physics video. In this video we're looking at section 2.2 part 2, which is about factors that affect the rates of evaporation. So let's look at the first factor which affects the rate of evaporation, which is temperature. Let's imagine that you had two containers of an identical volume. On both of the containers, the lid has been taken off of the containers, and we would fill both of these containers to an equal volume of water. So we can see that both of these containers have an equal level of water, which is at this point. This will ensure that the experiment is going to be controlled and the variables that are not being tested are going to be controlled, and we're only going to change the temperature of these two liquids, which will be our independent variable for this experiment. For the container on the left, we're going to say that it's going to be at room temperature because we're not heating it to any certain temperature. So room temperature would be about 26 degrees Celsius. For the second container on the right, we're going to heat it to a temperature of 80 degrees Celsius by using an electric heater, which I've drawn here. Now a question to ask ourselves in this experiment is, how does the evaporation rate vary with the increasing temperature? So in the first scenario we had water which was at 26 degrees Celsius, and in the second container we had a greater temperature for that water which was 80 degrees Celsius. To answer this question, we're going to look at both of the liquids and how their particles are behaving as the surfaces of each liquid evaporate. In the first scenario, we will see that the particles in that container will be in their liquid state. However, on the surface, the kinetic energy of the particles will be greater than the particles that are at the bottom of the surface. So we can see that these two particles above the surface of this liquid have greater kinetic energy because they have escaped from the surface of this liquid. We know that this isn't boiling point, and this does not mean that we're boiling this liquid right now. In fact, the water on the surface of this liquid is evaporating. We know that 26 degrees Celsius is a decently low temperature for evaporating a liquid, so if we compare to 80 degrees Celsius, we must expect more particles escaping from the surface of the liquid. So in the second container, we can see that the particles have greater kinetic energy, and the states are still similar to the previous one in the liquid because the particles are still close together. However, closer to the surface, we can see that the kinetic energy of the particles has increased, and above the surface of that liquid, the particles are evaporating more quickly than this lower temperature over here, because these four particles that are above the surface of the liquid have greater kinetic energy as compared to these two particles. So if we were to increase the temperature of this liquid from 26 degrees Celsius to 80 degrees Celsius, we would expect more kinetic energy in these particles, and there would be more likelihood for the particles on the surface of this liquid to evaporate. The particles on the surface of this liquid at 80 degrees Celsius will have enough kinetic energy to escape from the surface of the liquid such that they can avoid the intermolecular forces of attraction in this liquid. Whereas if we compare it to this liquid, we can see that the intermolecular forces of attraction are greater as compared to this liquid because of a lower temperature, and the kinetic energy of these particles will also be lower, so they won't be able to escape as quickly as the higher temperatures. So a quick way we can describe this relationship is that if we increase the temperature of the liquid, then the evaporation rate in E will increase. E is not the actual term for evaporation, that's just the letter that I use to represent evaporation. Now let's talk about the second factor that affects the rate of evaporation, which is the surface area of the liquid. Let's imagine that you had two different containers that were filled with the same volume of water. Let's say that the first container on the left was like a rectangular prism that was standing vertically, while the second one on the right was a rectangular prism that was standing horizontally. We know that in these two different orientations, the surface area of the liquid in this case and in this case will be different from each other. In this case, the control variables for the experiment are volume and temperature. So let's say that both of these containers had water filled to a volume of 500 ml, whereas the temperature of the liquid was 26 degrees Celsius in both cases. So by assuring that the temperatures of the liquids are the same, we can say that the temperature will not have an effect on the rate of evaporation, and we also have the same volume to keep things consistent. So the question to ask ourselves is, how does the evaporation rate vary with the surface area of the liquids in the two cases? Well, for the case on the left, we can see that we only fit 7 particles on this side of the surface area of the liquid, whereas on this one with the bigger surface area we fit about 13 particles on the surface area of the liquid. So in the first case we can see that we will have 7 particles evaporating from the layer, whereas in this case we will have 13 particles evaporating from the surface. So we know that if we increase the surface area of the liquid, then more particles will evaporate from the surface of the liquid as compared to the smaller surface area where less particles will evaporate from the surface of the liquid. So to finalize our understandings, we can say that if we increase the surface area of the liquid from this case to this case, then the evaporation rate will also increase as more particles will evaporate in this case as compared to this case with the lower surface area. Now let's talk about the third factor that affects the rate of evaporation, which is the humidity of the air that surrounds the liquid. So once again, let's imagine that you had 2 equal containers that were filled with the same level of water, and they had the same volume. And we know that if we don't keep the temperature the same for both of the cases, then the evaporation rate could be affected. So let's keep the temperature of both of the containers filled with water the same as well. Let's say that both of the containers are at a temperature of 26 degrees Celsius. Now since the containers that we're using for this experiment are identical in both cases, we can say that the surface area of the liquid in the 2 cases is going to be the same. Now the question to ask ourselves is, how does the evaporation rate vary with humidity? Well, before we talk about the particulate nature of the humidity in the 2 cases, let's first talk about what humidity even is. Generally, humidity is the concentration of water vapor that is present in the air that surrounds these 2 containers. Now, I'm not going to talk about the specifics of humidity because we're just experimenting how humidity affects the evaporation rate of the 2 containers. So from the definition of humidity, we learned that the air that surrounds the 2 containers that are filled with the water have some water vapor. And we know that water vapor is just a gaseous state for water, so we're going to have some gas over here. And we know that gases have very high kinetic energy, so I'm going to put 3 lines for the particles with the gas. So qualitatively, let's say that in the first scenario on the left, the humidity level is low as compared to the second scenario on the right, in which our humidity level is higher. And we can tell that the humidity in this scenario is less than this scenario because there are less water vapor particles in this volume of the air as compared to these greater number of particles of water in this volume of air. So the concentration of water vapor in this area is less than this one. Now as the particles in these 2 containers evaporate from the surfaces of each liquid, we know that they will collide with the water vapor particles in the air that surrounds them. We know that the particles over here are less concentrated in the air, so there's less chance of these particles colliding with these particles and going back into the liquid and condensing. Whereas in this case, the particles that are evaporating have a greater chance of hitting the water vapor particles and being collided with, and then going down back and condensing into the surface of the liquid. So we can say that because the concentration of the water vapor particles in the first scenario is less as compared to the second one, and because the likelihood of the collisions between the evaporated particles with the water vapor particles in this case is less as compared to this one, the evaporation rate in this case will be lower than this one. So to summarize, we can say that if the humidity or the concentration of the water vapor in the air that surrounds the surfaces of the liquid increases, then the evaporation rate of that liquid will decrease. And because of the inverse relationship, we can also say that humidity is inversely proportional to the evaporation rate. And this is it for section 2.2 part 2. Leave a like if you found this video helpful and you now understand the factors that affect the rates of evaporation. Subscribe for more videos in the future, and I'll see you in the next video. Peace out.